All right, let's try to get through another one of these. It's kind of hard to know where to start. I honestly don't know what I'm doing, but I feel obligated to just keep going. No one else is talking about this really. I mean, there's a handful of other people, but I'll try to keep it as simple as possible on this, but you're going to have some general knowledge. I'm not going to be able to explain everything cuz I can't make long videos. Like that's just not happening. Um Last week, I did want to tell a story first. Last week, my dad called and said, you know that big tree that's between your brother's property and yours? And I was like, yeah, I think so. He goes, I was thinking about cutting that thing, and I was like, don't cut that tree because it's a big tree. It's like a 300-year-old tree. He was like, your brother told me that I could pick any tree I wanted, and he's like, that's a good one. It's easy to get, and I was like, that is a huge tree. Let me look around. So I looked around on Facebook and found some people that some trees blew over. So we went over there and got some wood instead of him cutting some. I mean, he's 67 years old. He don't need to be cutting trees down, especially a tree that big. And plus, it's a nice tree. It's an old tree. Anyways, while we were there, we saw some yellow jackets flying around. There was a nest in a hole in the ground, but they weren't mad or anything, but they were stirred up. It was weird. It was like they were leaving their. It's like they were done. They were dying before winter. Like the queen had done left, and they didn't know what to do. I don't know. They just flying around. Well, we went ahead and finished the wood. I we come home. I unloaded the wood with him, and then I came to my house. Uh, so this was like a good 2 hours, 3 hours before since I had seen the yellow jackets. But I unlock my door and take out the stuff out of my pocket, my keys and whatnot, and just the routine of when I get home, I take all my stuff out of my pockets and put it into a basket. Well, while I was doing that, I get stung in the back by a yellow jacket. I rip my shirt off real quick and I find a yellow jacket just balled up inside there. I guess I carried him all the way home. Anyways, it gets worse. So after this, I take my dog across the street to do some mushroom hunting. There's a large patch of national forest, so we just go up there and give him some exercise, and I look for mushrooms. And anyways, while we were walking, I run into I find a mushroom on a tree. I stop and look at it, and I'm like, I'll come back and check this tree in a couple days. I've just taken a note of it, and while I'm looking to see how many other mushrooms or if there's any others, I get stung by another yellow jacket, and then I get stung again, and then a giant swarm just lands on me, and I have to start running like I'm sprinting through the woods. Um, I dropped my sunglasses. I dropped my phone. I was talking to my friend on the phone, but I just threw him down because I was having to smack yellow jackets, and they were stinging me through my shirt. I ripped my shirt off, and uh, they started stinging me worse because they were all over my shirt. There was like 20 on my shirt. I looked down and there's just all kinds of yellow jackets all over it. So that's when I ripped my shirt off. But then the swarm was still on me. Like I've never seen such aggressive yellow jackets. They were the most aggressive yellow jackets ever, and I had sprinted like 100 yards, so I had to sprint again. Especially without a shirt, it was terrifying because I couldn't put the shirt back on because there was yellow jackets stuck on it. So while I'm running, I'm like picking the yellow jackets off of it. Anyways, it was a traumatic moment, and I definitely wanted to share that with YouTube. I hope your days are filled with as much adventure as mine. So let's get back into the universe is not expanding, I suppose. I really don't like talking about this. I really don't. Like it gives me anxiety, the whole thing. Um but you know how this is. This is one of them things to where everybody's going to think I'm crazy, like I'm a crazy person, but you have to just pay attention to what I'm saying. Let's just get into it. I guess I'll go ahead and control. Oh, I have to click. That's sad. I hate mouse clicks on the microphone. Anyways, this is the start of it. First of all, the first thing you need to know. Oh, my heater just kicked on. Let me turn that off. Hold on 1 second. You don't want to listen to that in the background. It'll take a second. I'm sorry. I'm not cutting that out either. You just have to deal with it. Um, it'll cut off in a minute. General relativity does not predict the Big Bang. That is the most important thing for you to understand. Is that the Big Bang is not a prediction made by general relativity. General relativity can be used to model any number of universes. There are lots of exact solutions to the field equations. There are lots of different ways of modeling the universe. Cosmology is not an exact science like a lot. Like, sure, it should be an exact science if you had super duper computers that could scan the universe and put it all in a math equation, I suppose. But it's not an exact science for humans. It's way too complicated mathematically. So general relativity is what is typically done in cosmology. Are lots of assumptions and shortcuts and generalizations just to be able to get the job done. That's why general relativity, you're able to actually work with it, is because you're simplifying everything. Um, Good. The heater finally cut off. Does that sound better? I hope so. Um, Meanwhile, I'm getting cold, which is weird because the heater was just on. I think it's a psychological thing. But current cosmology, uh, current cosmology uses several different metrics, but the main one is the what is it? FRLW, Friedman, Lemaitre. I'm not going to go through it. Uh, I'm forced to Robertson Walker. I think that's right. Yeah. So it's FLRW. Well, I guess it doesn't matter what order you put them, but this metric uh, uh, is is just a way of modeling the universe. Like I said, there's multiple ways of doing it. It doesn't necessarily mean that it predicts the Big Bang because you have to match it up with the current parameters. Now they claim that it matches well, but it doesn't. Well, it does in a certain sense, and I'll get into that in a second. But that's the most important thing. If everybody's on the same page, we'll go on to the next slide, please, Jamie. Do you know what that is from? Next slide, Jamie. Next slide, Jamie. Does anybody know what this is from? Next slide, please, Jamie. It's Randall Carlson on Joe Rogan. That's have y'all listened to that one where he goes through the slides? Oh my goodness, I love that episode. But he's just the way he says next slide, Jamie. I love it. Randall Carlson is an amazing human. I love that guy. But let's get back to the universe is not expanding. One of the biggest mistakes that the um, mainstream cosmology and frankly all of the attempts at modeling the universe using general relativity, one of the biggest mistakes that the authors make is that they assume the universe is homogeneous. Well, it's obvious that the universe is not homogeneous. Let's go back to this other slide. Can I? Yes, I can. Right here. Obviously, the universe is not homogeneous. I guess the brain neuron looking things. This comes from I took a little piece out of the Max Planck Institute photo of the macro universe. It's the purple one, and then I just added the red color just for shits and giggles. But but you can see. I don't know if you can see the cursor. Yeah, you can see the cursor. Hopefully, you can see my mouse cursor. I don't know how this works, but I can see it on the other screen. But you can see that the universe is not homogeneous. This is not homogeneous. This is not homogeneous. Homogeneous would be everything has the same density. Well, obviously that's not going on here. So why is homogeneity assumed? Well, I kind of get it if they think that it's like a cloud of dust, then it's kind of homogeneous. Okay, fine, but it's not a cloud of dust. I mean, we're talking galaxies with black holes in the center, stars. Like, the universe is definitely not homogeneous, and the range of mass distribution, like it can be extremely dense, like in a black hole, or it can be nearly empty, like in empty space. But there's really no such thing as empty space. Even empty space is going to have some mass. And guess what? It's going to be fairly significant sounding when you're talking about the macro universe. Um, so, next slide, Jamie. The universe is not homogeneous. I think we've went over that. Like, but the universe is structured in a way. Like, you need to understand this. It's structured in a way that it's not homogeneous, but it's structured in a way that is gravitationally significant. Okay, um, and that's because all gravitational boundaries are just arbitrary. We'll get into this one in a second. Mass density is inversely proportional to the chosen volume. This is important, okay? Mass density is inversely proportional to the chosen volume. So these are just different scales um, of the universe. So up here in the top left corner, I just have a ball. I guess that represents a planet or something. I don't. It's just a chunk of mass. Okay. You can have the density of this, whatever. This is the range. This in the star range. Um, is where there's deviations from the rest of the universe because we're talking about these are the smallest scales. Yeah, I mean, we can go into atoms and things like that, but cosmology doesn't care about atoms, not at this point. We're just worried about gravity. Let's try to wrap our heads around gravity first. So, when I say that the universe is not homogeneous, that density is in fact inversely proportional to the chosen volume or the chosen radius of the volume of the chosen or the radius of the chosen volume, it means that on this largest scale here, okay, say this one on the, the bottom, these veiny looking regions. If you just draw a boundary, and just an arbitrary boundary around some area. Okay, just draw some random boundary around some area. The radius of the volume of that boundary is inversely proportional to the density, or the density is inversely proportional to the radius. However you want to say it. Have I confused you yet? I feel like I'm doing a terrible job explaining it this way, and that's because the reason that I think this, and it is because it just seems obvious. Okay, if you draw boundary, a large boundary right here, the density gets smaller. Now, if you know anything about cosmology, you'll know that this is true. So the largest scale, say the observable universe, has the lowest density. Okay, the smallest scale, say the galaxy, a galaxy would be the highest density. And so this is a special structure. This is why you can't use homogeneity. Now, see, all of these uh, solutions to to the field equations in general relativity, they all assume the universe is homogeneous or nearly homogeneous. But you have to know that the density is inversely proportional to the radius, because on the largest scales the density is going to be very low, and on the The other scales, the density is going to be high. The mass density is going to be much higher on smaller scales. This is important because that is the cosmological constant. That allows you to have a stable universe, okay? And that's because collapse time is directly associated to mass density. And so if you increase the radius, the time to collapse, in other words, like if the universe was going to collapse in on itself because of gravity, increases. So the larger the radius, the slower the collapse. That is all that's important, really, from using general relativity in cosmology. You can't do too much with it. You honestly cannot do too much with general relativity in cosmology. There are definitely things you can do in astronomy, and even obviously with the galaxy scale as well. There's um there's plenty of things that you can use general relativity, but as far as just uh, uh using general relativity for the entire universe, it's just not something that has necessarily been grappled with yet. Not well. It so far has been a failure. I think that the Hamiltonian method is probably the best way to do it. But once again, you have to have this inverse relationship with density in order for it to work out. Um, it also plays a role in the gravitational redshift, which is the next thing. So have we covered this? All gravitational boundaries are arbitrary. This is important also. Um, and that it's just what we call a star is just a clump of some mass. It's all part of the same object. It's called the universe. It's just when we divide it into these little sections, but we call things stars and galaxies. But they're really not stars and galaxies. They're just segments of the universe. I mean, you can call it a star, I guess. That's fine. But mathematically, the star doesn't know that it's any different than the rest of the universe. It doesn't have its own parameters. Like we pretend it has its own parameters, but it's not really. And the reason for this is because there are objects larger. The reason this is important is because there are objects that are larger than stars and planets and galaxies. I don't know what you call them, okay? Let's go back to the beginning slide. Whoops. I've got to go all the way around, I guess. There we go. So, there are objects larger than galaxies. What do you call this object over here? This thing right here. Vein. It's what neurons. Like, what do you call these? You could call this lightning. You can just name these things. The reason that I'm pointing that out is because that's basically what's been done for gravitational redshift so far. Calling this a galaxy and saying, oh, this galaxy has this amount of gravitational redshift, it's completely meaningless. It's completely meaningless. It's what they're really saying is that this galaxy right here would have this amount of gravitational redshift if this galaxy was in the universe without any other mass around it. There's no other mass in the universe. That's what the traditional equations for gravitational redshift is. Now, if you don't know, if you're still following along and you have no idea what gravitational redshift is, I'll explain. One moment. Okay. So one of the things that general relativity predicts is this thing called time dilation. Uh, and time dilation is this effect where the 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 metric surrounding massive objects gets warped. And so uh, one of the things that makes that warp in space detectable is that light will travel in through these what's called a geodesic. So these light waves will travel through these geodesics, which is basically just the shortest path between 2 points. And, you know, in Newtonian physics, the shortest path between 2 points is always a straight line. But with relativity, I don't know if that's true with Newtonian physics. I'm sure that there may be something I'm missing with that. But with general relativity, the shortest path between 2 points could be curved. I mean, it could be literally a curve, and so that geodesic would be curved, and la da da da. There's a lot more in depth to that, but you'll just have to read up on your own. So basically, here's the gist of it: light will be redshifted when viewed from a lower gravitational point. Light that was emitted at a higher gravitational or a deep gravitational well will be viewed as redshifted as it's when it climb if it's observed on the outside of that well. So in other words, this, let's say this is a star right here, this thing on the upper top left, this ball, light emitted from this ball and observed right here in the middle of nowhere. See, let's say right over here, there's nothing else. There in this area, there is no mass around it. So you have a flashlight here, you shine the light up here, this person will notice a redshift to this light. Now, if this ball is more massive, there'll be more redshift, okay? If it's a black hole, you won't see any light. The light will never escape it. If it's a black hole -1, it'll be extremely redshifted. Okay, are you following me? And let's not even include Earth or the Milky Way or anything like that at this moment. Just cosmologically, let's imagine you are in a place with almost no mass. It's like one of the least dense regions you can find. You are millions of light years away from other stars. Okay, so you're like in this one of these dark regions right here, and there's basically no stars around. Okay, let's say you view a star that's close to you, the closest star, you look at it, there's going to be a redshift. That redshift depends on what? Is it the amount of mass in the star? Yes, but what else? Maybe some mass around the star. Okay, right? Like if you view a star that's inside of a galaxy, yes, you use the galaxy's parameters, right? Because that would be the redshift. Okay, now this is where there's those gravitational boundaries or arbitrary argument, where that comes from. So let's imagine it's a cluster of galaxies like this one right here, or a supercluster, or a really dense cluster of galaxies, or this vein right here. So these objects that are larger than galaxies, call them whatever you want, these also will produce gravitational redshift. But find me a published article that talks about this. I want to know what the gravitational redshift of the great arc is. See, in cosmology, this is not ever discussed. I mean, sometimes it will be, especially in the context of dark matter. Like they'll do superclusters sometimes, or clusters of galaxies, the gravitational redshift of it. But for the most part, they think that, like, say, the Milky Way cancels out the gravitational redshift. But just imagine you're in the dark spot right here. What, like, you're going to have to use, say, you're viewing a star up here and you're right here in this spot, and you're viewing a star that's all the way up here. Like, wouldn't you use all of this? Would you not? Because you're in a spot that's the lowest density. This is the lowest density region in the whole spot. So you use this whole spot, right? Would you not? Like, tell me, experts, tell me, Neil deGrasse Tyson, answer this. Please, just answer this. Somebody send this to Neil deGrasse Tyson. This clip right here. If you, if someone is in a low density area, as such as this dark region right here, there's almost no mass in this region, and they are viewing a star that's in some region way over here. How much of this mass contributes to the gravitational redshift? How much of it? I don't like, to me, it's all of it. The rings of Saturn increase the gravitational redshift of light coming from Saturn. So I'm not sure how they skirt this. Like, if I was to say, if you were able to put any cosmologist on the spot, any kind of lambda cosmologist or expert in general relativity, and you put them on the spot with this question, would they admit to tire light? I don't know the answer to that. Regardless, this is why I think the universe is not expanding, because guess what? If you do this, if you put this in the basic equations, you can easily get Hubble's law. It's super simple, and the parameters match up with, in other words, the density at certain regions, whatever the volume is that you choose. You can, like, the density matches up with what is observed. To me, this is the simplest solution. All we do to get here is assume that the universe is not homogeneous, right? The universe is not homogeneous. The universe, the mass density is inversely proportional to the volume, I guess is the best way to say it. All gravitational boundaries are arbitrary. They're all arbitrary. A lot of people would disagree with that, and maybe it's the wrong way to say it. Maybe I shouldn't use the word gravitational boundary, but it's true. The gravitational boundaries are arbitrary. So if you're in a region and if you were able to look at the metric while you're in that region, the metric would look completely different if you're in another region looking at the other region you were just in. Good Lord, it's, it's really confusing and it's hard to discuss, especially because I don't necessarily know who I'm talking to. Uh, a lot of you, have zero knowledge of physics and cosmology. Some of you have some knowledge, and some of you may be experts. And so, like, I kind of have to talk to all of you. I don't really know how to do this, but uh, sure. Where are we at? Let's go to the next thing. Mass density is inversely proportional. Gravitational acceleration is relatively uniform across cosmological scales. So this is how you would do the general relativity. If you were trying to solve for Einstein's field equations, you would just have a uniform gravitational acceleration. That would help you keep the density inversely proportional to the radius, because those are the same thing. Okay. And for my calculations, it's something to the order of uh, I don't know, 7 times 10 to the negative 10 meters per second squared, something like that. Let me make sure that I said that right. 7 times 10 to the negative 10 meters per second squared. It would be the gravitational acceleration of the universe. It could be less than that. It could be more than that. It really just depends on uh, how you find a starting parameter. I'm not sure how you would go about finding a starting parameter. I suppose the galaxies at the very far reaches of the universe would, but if the universe is expanding and I'm wrong, then that really wouldn't help you out. But somebody needs to pick this ball up. I don't like, there's no way I'm going to get published. Like, no, like this cosmology, this establishment, this global establishment does not allow publishing outside of the accepted paradigm, and that's across all schools. And so, in order to publish something like this, you would have to publish it within the lambda paradigm, and I'm not sure how you do that. I'm not sure how you do that. Now, sure, go ahead and do. Maybe someone could adjust the Friedman metric, or the Friedman equations or something to have inverse. Um, uh, proportionality to the density and radius. But if somebody could do that, then that'd be great. I honestly can't hardly keep up with general relativity. Like the math is just ridiculous. So somebody smarter than I will have to do this. I don't know. But to me, you can't just assume homogeneity, because that breaks everything, and you're basically just doing the equations for no reason. The Hubble shift is gravitational redshift. I think we've arrived here. What else do we have? Yep, we're 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 pretty well covered everything that I know. Like this is not everything that I know, but this is the most basic parts of it. Like there's nothing to this. It's so simple. It's so simple. Anyways, I love you guys. I hope everything is wonderful in your neighborhood. I hope everybody's safe from the hurricane. Get ready for winter because it's coming. Um, anyways, y'all have a great night.